Okay, so we're doing problem 2 of homework 6. So problem 2 asks us if we're given these identical independent random variables, what is the PDF if for this, for A, and then we have B, C, and D. So for A, it's x plus y equals z. So what does that mean? That means big F of z equals probability that z random variable is less than or equal to z, and we can just substitute the x random variable plus y random variable in here. So the probability of x random variable plus y random variable is less than or equal to z. And what is that? That's the integral of little f of xy dx dy over this area. So we can express this as a line. So we look at the inequality x plus y less than or equal to z, and we solve for y. So I move x over, we get y is less than or equal to minus x plus z. So what's that? That's just a line with a slope of -1 and y-intercept z. So I put z over here. We have the line here. It crosses the x. So when y is 0, we have x equal to z. So these are the intersection points for the x and the y. Now, because the PDFs over here are multiplied by the step function, that means that x random variable and y random variable cannot be less than 0. They're always going to be greater than or equal to 0. So that's why we're only concerned with y less than or equal to minus x plus z only in the positive quadrant. So when x is greater than or equal to 0 and when y is greater than or equal to 0. So that's why I only care about this shaded area over here. Because x can never be negative and y can never be negative because of the original function. So now we come down here to find big F of z, so we can ultimately find little f of z. So big F of z is just this integral, as we wrote before, but because x and y are identical independent random variables, we can split them up into this, so this can become this becomes little f of x times little f of y of y. So we just do that, and in the next piece here we write them in. So little f of x is e to the minus x, and little f of y is e to the minus y. Now I drew this picture to help me figure out how I want to integrate this shaded area. So first I'm going to integrate with respect to y. So I'm going to go, y goes from 0, y equals 0, to this curve. And this curve is y equals negative x plus z. So the limits for the integral for y is from 0 to minus x plus z. And then we integrate with respect to x. X goes from 0 to z. So that's why the limits are 0 to z. So now we carry out the integral. So I write the x integral from 0 to z, e to the minus x, because that's not affected by the y integral. The y integral gives us minus e to the minus x plus z plus 1, because it's minus e to the 0. So now I'm just cleaning this up here a little bit. We have e to the minus x minus e. I distributed the minus sign, so it's minus e to the x minus z plus 1. So now we multiply through. So that's going to give us the integral from 0 to z of e to the minus z, and I'm going to split it up into two integrals, dx plus 0 to z of e to the minus x dx. Okay. So now we just integrate normally. This is a constant, so we can pull it out. So we get e to the minus z, and then we get, oh, I missed a minus sign. There's a minus sign here. So there's a minus here. And then we get what? We get z minus 0 for this integral. here we have a minus e to the minus z, minus minus becomes plus 1. So we multiply through here, so we get minus e to the minus z times z. The 0 doesn't matter. Here we get minus e to the minus z plus 1. So I can pull out e to the minus z because it's a common factor. So I take out e to the minus z. I'm left with minus z minus 1 plus 1. Let's see. Right. So then, this is big f of z, but we want to find little f of z. So little f of z is equal to the derivative of big F of z with respect to z. So what's that? So we don't even care about the plus 1 because it's a constant. So we're going to look just at this guy. So we've got to use product rule. So product rule, let's take the derivative of the first one, which is minus e to the minus z times minus z minus 1, plus the derivative of the second one, which is minus 1 e to the minus z minus z minus... I'm sorry, this is not here. Just minus 1 times e to the minus z. So now what does this give us? Let's simplify it. We get z e to the minus z plus e to the minus z minus e to the minus z. So these guys go away, and we are left with z e to the minus z. And that is what our little f of z will equal for z greater than or equal to 1. So let me explain that. So we have f of z equals z to the e minus z, and this is for z greater than or equal to 0. So why for z greater than or equal to 0? Well, we know x is greater than or equal to 0, y is greater than or equal to 0, so their sum has to be greater than or equal to 0. And this PDF will be 0 otherwise. And that completes part A. So let me just... Okay, so part B, we are asked to find the PDF for this random variable here. So part A, we had x plus y. Here we have x minus y. So again, we can do the same thing where we solve for y. So that means y is greater than or equal to x minus z. Now we have to be careful because there are two different solutions. There's one for when z is greater than 0, and there's another one for when z is less than 0. So first let's consider the case where z is greater than 0. So y greater than or equal to x minus z is going to be everywhere above this line. However, we have to remember that we're only considering the case where x and y are greater than 0. So this is x, this is y. So we only want the place where x and y are both greater than 0. And that's going to be this area over here and beyond. So to find big F of z, we have to do the integral. So we have this dx, dy. Dx goes from, we go from 0 to x equals y plus z. And then dy goes from 0 to infinity. Okay. So it's going to be the integral of, I just wrote these here again just to remind what little f of x and little f of y were. So we have minus x e to the minus y, dx dy, 0, y plus c, 0, infinity. Now this equals, so we have to do dx first, so it's going to be, we have 0 to infinity, e to minus y, then we have minus the integral minus e to the minus y plus z plus 1, because it's a minus minus e to the 0 dy. So now this becomes the integral from 0 to infinity of minus e to the minus y minus z plus e to the minus y dy. Okay? So now I want to separate that into the sum of two integrals. So I take out in here, I take out minus e to the minus z, and what's left inside, because this is a constant, doesn't depend on y. So I have this in here, plus integral from 0 to infinity of e to the minus y dy. And what I'm left with, I have this outside because it's a constant. So then I have minus, the minus, we have 1 over, minus 2. But evaluate it at infinity first. Well, e to the minus infinity is just 0, so we have 0. And then we have a minus minus, right? Because we have minus from the integration and minus from here, so it becomes a plus. E to the minus 0 is just 1 over 2. Forgot the 2 because when we integrate this, we bring down the 2. Okay, plus. And similarly, we have the same thing here, except we have a minus 0 is just 0 because at e to the negative infinity is 0. And then e to the minus 0 is 1, so we have minus minus becomes plus 1. So this turns out to be minus e to the minus z over 2 plus 1. So that means that, I'm just going to separate that, little f of z is equal to the derivative of this. So what's the derivative of this? We take the minus down, so it cancels that minus, but we stay with the e to the minus z over 2. Now this is little f of z for z greater than or equal to 0. But now we have to consider the case where z is less than 0. Let me just... Okay. So now we got to consider the case where z is less than 0. So let me draw my little axes over here. So when z is less than 0, z will be here. So this point over here, we have to be careful. So remember, we have, again, y greater than or equal to x minus z. This is for z less than 0. So that means z is a negative number. So what's this point? That's the point when x is, when y is 0. Well, because z is a negative number, x has to be minus z. This is the point when x is 0. Sorry. Excuse me. So when x is 0, when y plus z is 0. Right? But z is a negative number, so y has to be minus z, which is a positive number. Here is the point when y is equal to 0, so that means x must equal z, which is a negative number. Okay. So, now the area that we have to consider is for this guy, x greater than 0, and y greater than 0. So that's only going to be in this region over here and beyond. So, big F of z is equal to this integral. Dx goes from 0 to y plus z, and y now goes from minus z to infinity. So it's a little different. 0 to y plus z minus z to infinity. And the way I got these points, because I was paying attention to the fact that z is a negative number. So in order for x to be 0, y has to be minus z, which is going to be a positive number, plus a negative number gives you 0, right? Well, a positive number plus the negative of itself gives it 0. So, and the same thing for this point over here. So that's how I got these points. And that's very important for the limits of the integration. So, now we do the integration with respect to x first. So we're left with this, this should be minus z. From minus z to infinity of e to the minus y, and we have minus e to the minus y plus z minus minus plus 1 dy. And now we can take out minus e to the minus z. And I'm separating this into the sum of two integrals. So we go from minus z to infinity of e to the minus 2y dy plus the integral from minus z to infinity e to the minus y dy. And now we're left with, we have the constant here, e to the minus z times the first integration is going to be 0, well, minus 0 over 2, but it's still 0. Plus, now we have, because we're dividing by minus 2, oh, sorry. I already took care of the minus, because the integration, you get a minus, and then here you have another minus, so it's a plus, so ignore that. This becomes e to the 2z because minus z times minus 2 is just minus 2z. Here, the first limit of the integration, we get minus 0, and then we add in the minus z, so we just get e to the z. And the minus minus is why we get the plus. So now this becomes minus e to the e to the z. So minus e to the let me see. Yes, this is correct because I put in the e to the minus z here, so 2z minus z just becomes z. So that's where that comes from. Plus e to the z. I have the over 2 here. And this just becomes e to the z over 2. So now little f of z is going to be the derivative of that. So the derivative of that is just itself, because if I derivative with respect to z, you just get 1, so it's just going to be e to the z over 2. And this is for z less than 0. So the complete answer, little f of z, is equal to, from before, e to the minus z over 2 for z greater than 0, and e to the z over 2 for z less than 0. And that is the PDF of that random variable. That completes part B. Okay, so now we're doing part C. So part C wants us to find the PDF of x times y, which is equal to z. So we remember that first we need to find capital F of x, f of z, and then from there we can find little f of z, which is the PDF. So big F of z is equal to the integral of z random variable less than or equal to z. Well, what's z random variable? It's x random variable times y random variable less than or equal to z. So over this area we have to integrate our little f of xy. So we can rewrite this condition as y random variable is less than or equal to z over x random variable. So that will look like this. This curve over here, this curve will be y less than or equal to z over x, y random variable less than or equal to z over x random variable. But we remember that x random variable and y random variable must both be greater than or equal to 0. So we're only considering the area that's shaded here. This area over here. That's the only area that we care about. So we want to come here. So big F of z, I'm going to integrate with respect to y first. So the limits are y goes from 0 to z over x. So that's the first two limits. And then dx goes from 0 to infinity. So I have here the little f of xy, e to the minus x times e to the minus y. That's equal to this. So I do the integration with respect to y. So that's going to be, we'll bring down the minus, and it's going to be minus e to the minus z over x minus, but we still have another minus, so it becomes a plus, e to the minus 0, so it becomes 1. This is what we're left with. So now what I'm going to do, I'm going to distribute this e to the minus x over. So what's going to happen, I'm going to have minus e to the minus x minus z over x dx, and I separate it into the other integral for the sum. So it's going to be an integral from 0 to infinity of e to the minus x. Now this integral is complicated, so we're just going to leave it in that form. And this integral here is just going to go to 1, because we're going to have a minus e to the minus infinity, which becomes 0, minus plus e to the 0 becomes 1. So we're just left with 1. Now to find little f of z, we need to take the derivative of this thing with respect to z. So that's going to be over here. So we want to take the derivative of big F of z with respect to z. Now, because the derivative with respect to z has nothing to do with the variable that's being integrated here, we can interchange the order of the integral and the derivative. The derivative of 1 with respect to z is 0. So what we're left with is the integral from 0 to infinity of what is the derivative of this guy with respect to z? Well, it's just going to be minus 1 over x. So we bring down the minus 1 over x, the minuses cancel, and we are left with 1 over x e to the minus x minus z over x dx. Now, before I circle this answer, I want to remind everyone that x is greater than or equal to 0 and y is greater than or equal to 0. Therefore, z random variable must also be greater than or equal to 0. So this holds for z greater than or equal to 0. So we could also write little f of z as the integral from 0 to infinity of 1 over x e to the minus x minus z over x dx times u of z, because it's only valid for z greater than or equal to 0. Z greater than or equal to 0. And that completes part C. Alright, last part, problem 2, part D. So part D, they want you to find the PDF for x over y. So that means big F of z is going to be integrated over the area where x over y is less than or equal to z. So I rearrange this so I can write it as y is greater than x over z. So because x has to be greater than 0 and y has to be greater than 0, we only consider this area over here. So where y is greater than this function, but only where x is greater than 0 and y is greater than 0. So big F of z is equal to this integral. Now I'm going to integrate with respect to x first. So x is going to go from 0 to what? X is going to go from 0 to this function, which is y times z. Right? Because y is equal to, the line is y equals x over z. So the x points are going to be y times z. Now y is going to be integrated from 0 to infinity. So this becomes integral 0 to infinity. Oh, I forgot here, I forgot my dy. dx dy. Sorry about that. I have e to the minus y. This integral, the x integral, is going to be minus e to the minus yz minus e to the minus 0, so that becomes plus 1. And then we have a dy here. So I'm going to distribute the e to the minus y. So I have integral 0 to infinity. We have minus e to the minus y. Right? So it's going to be minus y minus yz. So I took out the minus y, so I get 1 plus z dy. Then I have plus integral 0 to infinity of e to the minus y dy. So this guy is going to become what? It's going to become minus 1 over 1 plus z times times minus e to the minus infinity, which is 0. I'm sorry. 1 second. Right. Which is 0. Then minus minus becomes a plus. But we still have this minus here because we have another minus. So it's going to be this times e to the 0, which just becomes 1. So it's just going to be this guy. I'll you know what? I'll write it more explicit. Let's do that. So we have minus e to the minus infinity, right? And then we have minus minus becomes a plus. And then we have e to the 0. So it just becomes 1. But this minus survives. So plus this guy becomes 1 because we know minus e to the minus infinity is 0. And minus e to the 0, right? We have 2 minuses, which becomes a plus. So here we get a 1. So this goes to 0, and this goes to 1. So we're left with 1 minus this. So this becomes 1 minus 1 over 1 plus z. Okay, so little f of z is the derivative with respect to z of this guy. So the only place that has z here is this, so we want to take the derivative of this. So what's the derivative of that? Well, I'm gonna write, this can also be written as 1 minus 1 plus z to the minus 1. So it's going to be, we have the minus here. Right, so the minus 1 comes down. So we have a minus already. Then the minus 1 comes down. And then we're left with 1 plus z to the minus 2, which is in the denominator. We have this. So this is just going to become 1 over 1 plus z squared. Now remember, because x and y are positive, that means that z is also greater than or equal to 0. So this is is for z greater than or equal to 0. Alternatively, we can write little f of z as 1 over 1 plus z quantity squared times u of z, using the step function. So that is the PDF, and that completes part D.